Hello everyone! Welcome back for another exciting episode of Whose Code Is It Anyways?
Cut! Wrong show, Pragma!
Right. Sorry. Okay, take two, I guess.
Hey! That's my line?
Hello everyone! Welcome back to another exciting episode of...
Oh, cut. Your frames are all off. It's making me so dizzy.
Hello everyone! Welcome back to another exciting episode of Lighting for Video Games.
What are you staring at? A ghost?
Oh, right, I forgot to calibrate the camera today, didn't I?
Just say the line, please. For the love of God, please let this be the last take. Take 159.
Hello everyone! Welcome back to Lighting for Video Games. Today we'll dive into how light can shape mood, highlight gameplay, and make your worlds come alive.
Perfect! Yes! Finally! We're done!
Anyway, now that you've had a small taste of what goes into making these videos, thank you for all the continued support. I'm glad that you're appreciating the series and learning something from all of the extra effort that we put into these videos. In this video, we will first be going over some real industry tips and reviewing the other suggestions that CJ and Littlefish showcased in their shameful attempt at fame. We will later be doing as promised, and demystifying and reviewing Heartbound's light code with detailed explanations of how it works. And as always, providing other useful tips and tricks along the way. Today, we're going to learn how lighting can make your worlds feel alive, immersive, and cinematic. Lighting is often overlooked in games, and always pushed to the late production period, but it can also really make your game stand out. Not only can it set the mood, but it can also guide your player's eye and create an immersive, or some might even say, luminescent experiences.
Joke killer! He's a joke killer! I swear!
Today I'm going to teach you all about lighting in video games. From ambient glows to dynamic shadows. We're diving deep into how light brings our worlds to life. Assuming that nothing explodes this time, that is.
One time! That happened one time! Let it go already!
Never. Now, a lot of things didn't sit right with me when I saw CJ's light code video. The one thing that really grinds my gears is that they lied. Not only about the code, but they lied about why they needed to modify the code, then manipulated the code to break it, and then said, "Look guys, it's broken." Yeah, it's broken because you broke it. But I digress. His explanation certainly left much to be desired for as well. So I'm here to demystify whatever that was and give a much easier explanation and show a more common lighting solution. The first thing I'd like to show you all is called a blend sheet, otherwise known as a composite sheet. It's a useful tool that every technical artist or lighting or rendering engineer should know about. It shows you the entire composition of layers and their blending operations and the final effect all in one place. You start by taking a screenshot of your game and placing it in the first layer. I'll be showcasing both Littlefish's and the more common lighting solution using this blend sheet to explain them, instead of MS Paint. Down here we have the individual layers and their blending operations shown in real time, so that you can see exactly what textures go into the final result and what they do. I'll start by explaining Littlefish's lighting setup. Their setup uses 3 layers, the game screen, the subtractive, and the color layer, which means they're potentially drawing every light or shadow twice, for pretty much no reason. Even worse, this subtractive layer is meant to be grayscale, but what happens if we accidentally draw color onto it? Like a warm yellow for the sun or a fluorescent light bulb, for example. Well, let's try it. That's weird. We get this weird blue tint, isn't that strange? Well, not really, because what we're actually doing is we're subtracting the new color from the layer below, and yellow is made up of both red and green, which leaves only blue left over. Does that make sense? It's not really the most intuitive or realistic lighting. That's why he uses the color layer to tint the light, and uses the subtractive layer as a mask to shape that light. But you can really just shape the light texture with an alpha mask, making that subtractive layer entirely unnecessary. Here is the more common professional method. We use only one off-screen light map texture. Step 1. Fill it with an ambient color, like moonlight or fog, for example. Step 2. Draw your lights directly onto that surface. For the shape lights, I'm using a shape fill tool with a Gaussian blur filter on the layer. For the rays, I'm using a simple overlapped gradient, and for the canopy lights, I'm using a textured brush. Step 3. Draw your hard shadows with full or partial opacity. Step 4. Draw any dynamic occluders in your scene over that. You can also include things like ambient occlusion to really make your scene pop. This has the effect of erasing the light where it shouldn't be, and casting a shadow from the light, and boom! We have realistic 2D lighting with one single off-screen texture. That's what's called deferred screen space lighting, and that's how most modern 2D games do it. You can separate the light and shadow surfaces if you want, and draw them both onto the screen, but it's really not that necessary. And another nifty feature of the single texture solution, if you wanted to erase both light and shadow, you just draw the ambient color on top, which gives you full control over light and shadow in your game. Want to get creative? Reduce the resolution of the light map and turn off texture sample filtering, or use point or nearest neighbor, for that clean pixel light effect. You can also use particles as light sources for those flamethrowers or magic spell effects. Or use a noisy brush for the tree canopy shadows, or even use complete black for a fog of war effect. Here's a free art tip though. Real shadows are never pure black in the real world, because there is always some form of ambient light bouncing around, like the moonlight, for example. Unless that you are deep underground in a cave where no light anywhere can be found. This is why scenes in the void are often pitch black. There are tons of other tricks too. 2D normal maps for sprite-based surface lighting, grid-based flood fill systems like Terraria or Minecraft, or casting vector-based shadows for razor-sharp results. Each technique fits different art styles and performance needs. No one size fits all. And now you know how real lighting works, how to improve it, and how to bend it to your whims, and maybe even how to make your own lighting system for your own games or engine needs. Now I'm going to show you an old school technique for simple character lighting in 2D games that you can use without a shader. Now a long time ago, we used to use separated alpha mask bitmaps to determine the transparency areas of a sprite. In today's graphics formats, this is now known as the alpha channel. However, we lost some of the flexibility by combining the channels on which this trick depended on. And sometimes all you need for believable lighting is to think outside the mask. And you'll see what I mean by that very soon. First, create a new layer and select an area around your character. Make sure there's plenty of space around the character, about one tile or so around each side. Now fill this area in black, then select the opacity of your original character and fill it in white. Deselect the layer, and let's add a Gaussian blur to the layer and mess around with these numbers until it looks about right. 20 looks okay. Then change the layer's blend mode to multiply and turn on alpha clipping. If we move this layer around, it looks like there's a light in front of the character. But that's not all. Let's add a gradient map so that we can control that gradient. Everything that is on the left here will show where it's black, i.e. the shadows. Everything on the right will show where there's light. So let's choose a mid-purplish tone for the shadows. And as we slide it around on this gradient, you can see it fills more of the sprite. Let's choose a soft blue for the light, because the magic runes are blue. The closer the light and the shadow on this gradient are, the sharper the rim light. We can flip the gradient so it looks like the light is in front or behind the character. Right now it's behind. We can change the opacity of this layer to make it blend in more with our sprite as well. And as we move this layer around, if we move this layer opposite from the light's direction, it will simulate the light coming from that direction. Now let's take a peek at Heartbound's lighting. Well, what CJ showed, that's actually only half of the system. It simulates light wrapping around surfaces like the glow of the character's face, while another part of the code that lives in the light source somewhere else handles shadows using a mini 2D ray marsher, scanning every row of the light texture for an occluder and caching the resulting distances between frames. Then it draws the slices of the light texture from the edge of the light to the point where it hits the occluder. This has the effect of casting shadows just by not drawing the light behind the occluder. It's realistic in that regard, lightweight, and reuses the data if nothing changes between frames, so it's still fast without sacrificing the visuals. Some possible improvements we can make? Well, we already discussed how using a binary search and backtracking whenever we've gone too far is one option. If we were to also use rays and intersection math, it could be a lot faster than the pixel scan that checks for the occluders. Relatively speaking, of course, since this is on a pixel scale, the improvements to the speed would be so minuscule that they probably aren't even worth the extra effort. Another thing to notice is how the contours of the occluders are pretty much always the same for each frame. So we could just create a sprite with a gradient distance from the edges or cache it into an off-screen texture the first time that we calculate it, so that changing the cutoff range of the alpha will hide and show more of the rim light, treating the sprite like a signed distance field of sorts. You could also use the color channels of this texture for each direction. However, you'd have to do this for every occluder and their sprite frames. At that point, it'd probably be more worth it just to switch to shaders and normal maps, since they are more flexible and offer more fine-tuning of the surface direction of the sprite. I'm really only mentioning these things to give you more ideas of how to solve this problem in different ways, because if you ever do come across a bottleneck, having a few different ideas and tools in your tool belt on how to improve your performance is always a good idea. If you enjoyed this breakdown or learned anything, hit that subscribe button, ring that bell, and drop a comment on what you want to learn next. We've got more game development magic coming soon, and I promise, fewer bad lighting jokes in the future. Just wait until you hear the audio ones.